right, so we are going to talk about enols and enolates today. Correct. Yes, this will be for exam, I guess 4. Yeah. Oh, you're right. I did give a problem, didn't I? Okay, let's take a look. What class are you guys? This one. Okay. Let's see. Because I haven't thought about that either. So, all right, what are we going to do here? Okay. Interesting. All right, so walk me through this. Let's go ahead and do it. Let's copy this onto today's notes. Goodbye, enolates. We'll do them in a little bit. Okay. All right, so apparently I had asked y'all to do this. So what are we thinking in terms of synthetic routes here? I love how Andre is like, yeah, we have to do this problem still. And then nobody is ready to go. All right, so, yeah, right. So, what do we want to look at first here? What steps are we going to take to figure this thing out? I like that idea, and why did you choose to do that? Extra carbon, right. Big thing here, we have 5 carbons here, we have 6 carbons in this portion, that is. So that is a pretty good indicator that we probably want a nitrile here. Hold on, Bailey wants to go outside. Let me open the door for her. Okay. Okay, so good idea. I like that. And let's, I don't know, throw let's use a non-nucleophilic solvent. How about what DMF? Yeah, that'll work. Okay. Cool. All right, so now we have 6 carbons and a nitrogen. So what's next? What are we thinking to do? So we have the kind of left side, and we technically have the nitrogen. So we have 2 more things to do to it, really. Dibond would turn it into an aldehyde, and that would get rid of our nitrogen. So I would not use that as well. I mean, it depends. It depends what you're going to do, but um, I don't think making an aldehyde will be a useful thing to do right now. Okay, so if we did a Grignard, uh, what 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 reagents do you want to use for the Grignard? Like, what's your Grignard reagent going to be? Okay, so if we put ethyl Grignard in here, what do those do with? And then don't forget, we also need that acid wash. Oops, that would be number 2. So if we tried to do that, remember what happens is we end up with We're going to have all our carbons there. That's now going to be a ketone, and we're going to have our ethyl group, I guess, there. So is that closer to what we want? Yeah. Well, I mean, technically, if you don't do the water wash, it will end up as an imine, but even so, the nitrogen is now up here. So, we're not going to want that. So, okay. No Grignard. Let's try again. Although I think, hold on, I think Bailey has found some trash. Now she's going for that. What's that? Bailey, come back here. Yes, she was being naughty. Okay, you're staying in here, Missy. Okay, so, what what did you think about while I was chasing after her? Thomas had a suggestion. Let's hear it. I like that. The okay. Not acid though. Acid will protonate your amine once you're done. So just water. Just remember that part. Okay, and then acylation with what? Yes. What's our R group? Of course. Methyl one. Okay, which will give us then give us the following. And then what's that? Hold on, Eric, you're real quiet. Let me have to change your volume. Oh, and then just go and mute yourself. Okay. Go ahead. No, too shy, huh? So this is an interesting quandary we're in. Um, I like the idea of using the acyl chloride. By the way, you're going to need two equivalents of the amine, or you're going to need a base in there also. Just because remember that if you use the acyl chloride, you're going to need you need the extra base to take care of the HCl. So we can avoid that by just using the anhydride instead. Acetic anhydride is super cheap. Totally cool to use that. And that way you don't have to worry about using two equivalents because your byproduct is the acetate ion, which is not going to interfere with anything. So I like the idea of acylating. We're going to need to do that, but I don't think we should do that yet. The reason for that is because putting that methyl group on is actually the hardest part of this. Believe it or not. So just that silly CH3, that's the troublesome part. Can we just use a base and methyl iodide, just use it as a nucleophile and go and attack? Not really, right? Because we're going to end up polyalkylating, and that's not going to work. So we can't say, I don't know, what's a base to use here? I don't know. Butyl lithium as a base. Methyl iodide, we're going to end up polymethylating this thing, right? So, not an option. Okay, so how can we put a methyl group onto this thing? NHR2. You don't need two equivalents if you're using the anhydride. You just need one, because the second equivalent there is just to get rid of HCl, and since we don't have any CLs in the anhydride, we don't need to use two equivalents. Otherwise, if we did use the acyl chloride, we would need two equivalents of this thing, of our amine, if we wanted to acylate it. So using the anhydride just saves that step. So usually for acylating an amine, an anhydride is a little bit more useful. So I mean, this is something we will need to do, but I don't think we should do it yet. How can we take this thing and take it and turn it into this? How can we methylate it? Just a single methyl group. So remember that with a lot of these syntheses, there's really three ways that we make amines, right? We can use a nitrile and reduce it, which we have done here. We can use the Gabriel synthesis, but that you can only make primary amines of Gabriel. But if you want a secondary amine, there's only one way to do that, right? And that is reductive amination. If we remember that, if we want to put a carbon group onto an amine, onto a nitrogen, that is not an acyl group. Acyl ones are easy to put on, right? But if we want to put a methyl group or some other alkyl group, we need to use reductive amination. And if you remember what that is, that's where we are using our, we're going to see that, remember, reductive amination, you have some sort of carbonyl compound, some sort of nitrogen-containing compound, and then you have that, the cyanoborohydrin thing. Do you remember this? And that ends up making it so you can put a methyl group or some other amount of stuff onto your nitrogen. In this case, this bit, I'm sorry, that's our product. This will be our material here, right? So if you want to put just a methyl group on, we need to put a ketone or aldehyde that has, well, it's got to be an aldehyde, right? If it's just one carbon, that's formaldehyde. One carbon. So if you want to put a methyl group onto an amine, you're going to want to use formaldehyde acid and then this cyanoborohydrin thing. So that's what I would do first, and then we can go ahead and use our acetic anhydride and put on the acyl group. That'll be the way to do it. So don't forget, this is kind of your most useful way of making amines, because you're not limited to only making primary amines. You can make whatever sort of crazy amines you want. So let's restart the whole thing. I'm going to go vertical as well. So we have this. We went ahead and put our KCN in, and we used the solvent. What do we use? DMF? Doesn't matter. So we now have our cyano product. We went ahead and reduced it. So we have our amine. And now in order to install that methyl group, that's the pesky reductive amination business. So to put a methyl group on, this is ugly. Let's try this again. We need formaldehyde, bit of acid, and then cyanoborohydrin. That will put our methyl group on. And then, yes, then we can use our acetic anhydride. Again, acetic anhydride is better for this purpose because we only need one equivalent of our amine. Otherwise, we would need half of our product to be thrown away as the protonated form with the chloride. So that would be how we would make this molecule. So introduce the nitrogen through a nitrile because we need that extra carbon. We're going to reduce our amine. We're going to use reductive amination on formaldehyde to add a methyl group to our amine. And then we're going to use an acylating agent to put on our acetyl group there. So don't forget reductive amination. Very, very useful. Probably the most useful of the amine reactions. All right, so and the reason we don't want to do this beforehand is because if we acylate our amine before we put on the methyl group, it becomes much less reactive, right? Because then its electrons are going to be delocalized into the carbonyl, and so with that, it's not going to be able to react as readily for amination because we don't have an amine anymore. We have an amide at that point, and amides react very differently than amines do. So that's the methyl group is the tricky part here on that problem. Cool. I don't know if we have a name for it, but it's just what amines or how you can make amides. Amides are just essentially, you have some sort of thing, right? You would need two equivalents of your amine, and then you'd get your amide out. Or if you use the anhydride, you do not need two equivalents. You would just make your amide. And so there's not really a name for it per se. It's just our way of putting on our acyl group. So again here, the problem with using the acyl chloride is you need two equivalents of your amine. And since our amine is our starting material, it's hard to say that we'll have two equivalents of that, right? Because, typically if you have ammonia you're throwing in there, whatever, ammonia's dirt cheap, like go ahead, waste your ammonia. Not a problem. But like if you've spent all this time synthesizing this molecule and then you're going to lose half of it to being with the chlorine, it's kind of pretty wasteful. So generally acetic anhydride is used if you need to acylate an amine. All right, but if you're just putting ammonia or something, a simple amine on that's like cheaper, then yeah, you can just go ahead and use the chloride. But you just need to remember you need two equivalents of the amine. Cool. So it looks like we got some studying to do. So don't forget that. Alrighty, any more questions on this sort of thing? on this one or on reactions that we've covered? I do have office hours today, so if you have more, we can do more. Don't forget there are plenty of problems in Discord. In your extra resources tab, I put Mrs. O's SIs on these sections. So, and they actually do sync up with the keys. Remember, I've said that. So, practice, practice, practice. Alrighty. Cool. All right, let's let that sink in for just a moment before we transition to something completely different. So we'll let all the amides and all that go. Bailey, in the meantime, is looking at me like, why the hell aren't you letting me out of this room? She's being naughty. Okay. Cool. Let's get started then with the next thing, enolates. So, to transition to something completely different, we're not done with carbonyls yet. We've spent the last couple of chapters, excluding amines, talking about reactions that happen at the carbonyl carbon, right? We've seen that when we, sorry, Ms. Bailey, when we were looking at ketones or aldehydes or carboxylic acids or whatever, we were focused on this carbon. And we're going to see that now, in this chapter, we're going to be focused on this carbon. So we have a new focus for the chemistry that we're going to be talking about related to carbonyl compounds. So aldehydes, ketones, carboxylic acids, all those derivatives, we always focused on the carbon that was bound to the oxygen, double bound to the oxygen, right? But now we're going to be focusing on what's called the alpha carbon. So let's just do a couple of things here. We're going to see that all of these protons and their respective carbons do have special names. We call this position the alpha carbon. It is the one directly adjacent to the carbonyl. If this was a ketone, we would have an alpha carbon on the other side as well. It's just an indication of how many carbons away it is from our carbonyl. This one would be a beta, and this would be a gamma carbon. So the farther we go out, we just increase the letters. This is a terminology used extensively in biochemistry, where they talk about beta protons and gamma protons and whatever. Really, this chapter, we're going to be focused on alpha protons. This one here is not an alpha proton. This is an aldehyde, right? So this is an aldehydic proton. So we're not really going to focus on those. Those don't really do much. So we're not going to worry about that. We're going to see that alpha protons in particular are quite acidic. And that's going to be something that we're going to see is going to be very important when we look at the chemistry of what's happening at the alpha carbon. We're going to see that the pKa's of these are going to be quite low, and we're going to do all sorts of transformations there. We can install bromines there. We can install all sorts of different carbons there. We can do all sorts of fun stuff. And let's first start by talking about why these are acidic. So remember that acid strength is all about the stability of the conjugate base. And so if we were to compare by removing a few of these, if we were to take this molecule and remove a few of its protons, copy it a few times. Nope. No, go away. There we go. All right, I'm going to remove a few protons. And we'll draw their conjugate bases. I mean, gamma, who cares, right? Let's look at the aldehyde one instead. So, if we're looking at these three as potentially acidic hydrogens, if we're to compare their conjugate bases, we would go back to 105 material, and we'll remember we have the REO method, right, where we look at the atom identity, we look at the resonance, we look at inductive effects, and then we look at the orbitals that are involved. And so here we're looking at all of those things. If we're looking at the atom identity that all of these negative charges are on, these are all on carbon for all of these. So in terms of what the hydrogen is attached to, these hydrogens were all attached to carbons. So in terms of that, in terms of the atom identity, all of these are equivalent. If we look at resonance, and we try to resonate this thing, lo and behold, we can do that, which would give us, I'll just go vertically here. We end up with a negative charge on the oxygen instead. And so this is a more favorable resonance form, right? So we're going to see that this resonance is very stabilizing, so we have good resonance here. We're going to see with these ones, we have no resonance as an option, right? There's no way to resonate those lone pairs. If you look at the one that's on the beta carbon, the negative charge of the lone pair, you can't move that anywhere else without giving something 5 bonds. So, not allowed. And if we try the same thing with the aldehyde carbon, we're going to see there's nowhere for that to go either. When you have a negative charge on an sp2 carbon, it's better than sp3, but still not so great. And considering we have the oxygen with relatively high electron density, it's probably not very good to have it there either. So we're going to see that. With in terms of inductive effects, remember inductive effects are how close you have an electron withdrawing group to your carbon of interest where your negative charge is. I'm going to go vertical for this one. In terms of inductive, we have the induction right next to our negative charge, right? We know that electron density is being pulled, electron density is therefore going to be donated that way. No, I had it right. But that's not the induction I'm trying to show, sorry. The induction that I'm trying to show is that this carbon adjacent is partially positive. The carbon to carbon is partially positive, right? So we have some inductive effect stabilizing having the positive and negative nearby each other. However, of course, this is really insignificant compared to the resonance. So resonance is much more of an important factor in determining acidity. And if we look at inductive effects for the other ones, oh, I totally don't even have the right molecule drawn. If we look here, induction on the same carbon is bizarre. Not really helpful there. The induction on the other molecule is the same, but remember that induction becomes less and less important the farther away you go. So this is farther from the partial positive. This the one on the left is adjacent, and the one on the right is in fact on top of it, which makes it not partially positive at all, right? It's fully negative. So you have now two sites of electron density right next to each other that are bonking into each other. Not a good thing. And in terms of orbitals, we saw that this is sp3, sp3, and sp2. sp2 is slightly better. Remember, for negative charges, sp is ideal, then sp2, then sp3 for negative charges. So we have a slight advantage in the rightmost molecule, but it's not really nearly good enough to overcome the resonance and induction effects that the other two experience. So we're going to see that that aldehyde proton is not acidic at all. And really, we're only going to be looking at the alpha protons because predominantly of this resonance. This is our main reason. So it turns out, since this is the more common resonance form, we will often draw it this way, right? It's more stable because you have a negative charge on oxygen. That makes it more stabilized. We're delocalizing it. And so we're going to take a look at that in more detail. Any questions on why they are more acidic? Hopefully we can see like kind of this lovely chart we've made. You see that it's predominantly due to resonance, but we also have some minor inductive effects as well that are still better than the other two cases. The other two can't resonate at all. All right, so those are our acidic protons. Let's take a look at their pKa's. We're going to see that, roughly speaking, generally speaking, here, let's see if there's a nice chart on Google for us, because I don't want to recreate all this stuff. Yes. Go ahead. Wade, I think is chapter 3, maybe? Way back when. Alpha protons, pKa chart. Let's have a look at, this might have I just want a nice table. Perfect, that's what I'm looking for. Okay, so let me just switch screens on y'all real quick. So we'll switch to Google. Okay, and I'll put this, so that should switch us over. So if we're looking at some of these alpha protons, if we're looking at things that have alpha protons, we're looking at predominantly these two. Oh, I can't even highlight. Hopefully you can see my cursor. Aldehydes have pKa's on their alpha protons roughly of about 17. For ketones, we're looking at about 20. For esters, about 25. And we're going to see that if we have multiple carbonyls, those pKa's drop dramatically. And so it's important to note that all of these pKa's here, 9, 11, 13, are all below 14, which is a very important pKa for us. Why is 14 an important pKa? Do we have a common base that has a conjugate acid that's pKa is about 14? Maybe something that, wow, no one remembers Anything with a pKa of 14? He's so quiet. Okay. Go ahead, Eric. Try again. So let me switch back here. So, Eric, I can't hear you, whatever you're trying to say. You can type it if you want. Yes, indeed. He DM'd me. It's water, yes. You could have written that in the chat, but yes. Notice this magical compound here has a pKa of 14, right? So we're going to see, therefore, that OH minus is a good base for protons with pKa's of around 15 or less. So we're going to see that hydroxide would do a very good job of deprotonating something that has a pKa of less than about 15 or so. If you have a bit more than 15, you're going to probably be in an equilibrium situation. And if you're way above, say, 20 or so, it's probably not going to be a good choice. So, I thought about that. I'm still totally recording myself on Discord, so let me switch that window. So, because water has a pKa of 14, it's really an ideal base for things that are below 15 or so. And if we harken back, what's wrong, sweetheart? Okay. If we, I really should have just copied this. Here we go. We're looking at the alpha protons here. We're looking at pKa of about 17. If we look at ketones, we're looking at 20. For esters, we're looking at about 25. And then if we switch over to the dicarbonyl species, these protons down here, the pKa is about 9 or so. And if we have one as an ester, one as the ketone, or aldehyde, again, ketone or aldehyde doesn't really matter. Those are both going to be about 9. This is about 11. The aldehyde will be slightly lower, maybe towards the 8 side, but still roughly around there. And then if they're both esters, we're looking at about 13 or so. So these protons here. So, knowing these pKa is going to be very important because this tells us that water or hydroxide can fully deprotonate these. And hydroxide here, I wouldn't even use it with the ester. Instead, you're going to probably just hydrolyze the ester. But we would probably have an equilibrium going on here. And so if we want to remove the protons, it's important that we choose our base wisely. Hydroxide is a nice base because it's relatively safe, except as we saw when we pour it on our skin and our skin starts to dissolve in the saponification type idea. We're going to see that with these alpha protons, when we want to deprotonate them to do something, it's important that we choose our base wisely, right? So hydroxide is great. If you can use it, you should. All right, because it's a safe, relatively safe base. We're going to see that in order to really get these left three to go, the aldehyde, ketone, or ester, just the mono form of all those things, we're going to see that we're going to typically want a stronger base. So if we want to irreversibly or fully deprotonate them, we're going to want to use a stronger base. So use hydroxide indiscriminately with the things on the right. The diketones, the keto esters, or the diesters, use those with OH minus. All right. For the plain old aldehyde ketone ester, you can get away with hydroxide if you are okay with a slower reaction. But if you want an irreversible reaction, you're going to want to use a stronger base. So our stronger bases here are going to be H minus, as in the form of NaH or KH. Remember that H minus as a base, remember it's never a nucleophile, it's always a base, comes in here, kicks up our thing. This is not reversible. We end up with the negative charge here. So we have 2 protons left on that side. This is irreversible because we make H2, H2 bubbles away, and it's gone. It has launched itself into outer space. So this is an irreversible transition. So if you used NaH, for example, you would have the sodium salt of your what's called an enolate. We'll talk about that in a second. But I want to show you another strong, commonly used strong base. So hydride is a good strong base, a little bit less safe to use than OH minus. This one is water sensitive, and there's all these other considerations. So because it's a stronger base, it's a bit less safe, right? Because it's going to be more reactive. So that's one way to do it irreversibly. Another way is to use LDA. LDA is lithium. Lithium. I guess this would be, because it's negatively charged, we'll have it that way. We're going to have the 2 isopropyl groups here, as well as a negative charge on our nitrogen, positive charge on our lithium. This is a super strong base, just like hydrogen is, because the pKa of this dude, like most amines, is about 35. So if you think water as a pKa of 14 is a good choice to deprotonate anything with a pKa less than 15, rather the base of it, hydroxide, LDA will work for anything with about 36 or below, a pKa of 36 or below. So if you imagine all these pKa's, the highest we have is 25. That's a 10 to the 11 difference, which means irreversible. So if we use LDA as our base, we can go ahead and use that. Let's take a look. Let's use a ketone, let's use an ester this time. We're going to see that the mechanism for the acid-base reaction would be just the same. We want this to react. It's just exactly the same as before. We end up making our conjugate acid and the corresponding enolate. So good choices of bases for your less acidic protons. So your ketones and esters, you'll probably want to use H minus or LDA as your base for deprotonating. For the rest, even aldehydes, you can get away with using hydroxide. Because I think if you go ahead and look at your aldyl condensation, you use hydroxide for that, and you're actually using a ketone, so you're going to have it in equilibrium. we'll take a look at that in a sec. This is also an irreversible reaction. Although, if you use an equilibrium style base, hydroxide, with something like a ketone, pKa of 20, because of that equilibrium, you run into some problems, potentially. So let's take a look at that. So with these irreversible ones, you go fully all the way to your enolate. And so we're going to see how those are going to be used later on. All right, any questions on these acid-base things? So it would be a good idea to you don't have to memorize these, of course, because open notes, right? But it would be a good idea to have these categorized in your brain, at least. Having the 2 ketones or 2 carbonyls, hydroxide will pretty much fully deprotonate your substrate. If you use a monocarbonyl species, you're going to typically need a stronger base if you want it irreversibly removed. If you're okay with it in equilibrium, then you can use hydroxide. Although typically, again, we're not looking at that too often. So let's take a look at what that might look like. Let's take a look at acetone. If we go ahead and deprotonate, we're going to see that this is an equilibrium that heavily favors the reactants. And so that means, and I don't need to draw that, we're going to see that the pKa of water is 14, pKa of the ketone about 20. So we have about a 1 out of a million, chance of this happening, 10 to the 6th power. So we're going to see that as a result, the equilibrium will heavily favor the acetone and hydroxide versus the enolate and water. And this is a problem because we're going to see that this dude is going to be strongly nucleophilic. And it will just go ahead and attack a different acetone molecule. This doesn't happen when you use the strong base because you don't have any acetone left to be attacked. If you used hydride, your hydride is immediately going to react with all your acetone present, and all your acetones will be converted into the nucleophilic form, the enolate. The enolate is strongly nucleophilic, and if there are no nucleophiles, it's just going to hang around. However, we're going to see later on when we learn the aldol reaction that ketones and aldehydes make great electrophiles, right? We've seen that. And so if you have an equilibrium base present, those are going to react with themselves. And so you end up having some additional reactions happen. So just beware of that, because this is an electrophile, right? So we're going to see later on that this will react with itself. All right, so we're going to see that the choice of base is very important. That's what I'm trying to hammer out here. So if you don't want this to react with itself, sometimes you do. Absolutely, the aldol reaction is extremely useful, synthetically speaking. But if you don't want the aldol to happen, if you want to do other things with your enolates, you're going to want an irreversible base like H- or LDA. If you do want them to react together, go ahead, use hydroxide. That's a great idea. So it just depends what you want. Okay? So just keep in mind, this is a 10 to the 6th to 1 ratio. that you'd have. And since you have a strong nucleophile, you have so many more, you have 1,000,000 more acetones for every enolate you have, it will just go ahead and react. So we're going to see that reaction later on. Okay, so we look here though, pKa is 25, 35. In this case, we have 10 to the 10 to 1. So we see here that all of it is the enolate form. There's nothing left for the enolate to react with. So do we see why these are considered irreversible? 10 to the 10 power. That's what, 10 billion? So yeah, there we go. So that's the whole point of all this stuff. All right, so any kind of questions on the idea of choosing your base? Yeah. Depends what you want. So if you want it to be irreversibly converted into the nucleophile form, the enolate, yes. Strong base, better. But if you if you want this to react with itself, or if you have an aldehyde that's also present in the mixture, then the hydroxide's fine, and it's a better choice because it's not like explosive like some of these bases might be. So it's important that you choose the the correct form, if that makes sense. So use the LDA or H minus when you need to. Use the OH minus if you can, if that makes sense. So if if OH minus is an acceptable base for your reaction, you should use it over choosing your stronger bases because it's safer. However, if OH minus will give you weird products, don't use OH minus, right? So use the strong bases if you have to. And so this chapter, it's we're going to learn kind of the times that we will use one over the other. All right, so that'll be a big determination in whether your reaction will be successful or not. Is your choice of base. All right, so does that kind of it takes the question that says we'll answer it later, and I hope that's okay. So in the meantime, though, we'll take a look. So these are enolates. All right, these are positively charged or negatively charged things. We also have enols, which are different. We see that an enol exists in equilibrium. This is a ketone. This is an enol. En for the alkene, ol for the alcohol. Underlined the wrong thing. That's where enol comes from. This happens with this kind of catalytic base or acid. You can form the enol. It's typically not very favored. Ketones are generally preferred over the enol. And it's important that we talk about this because apparently, remember, you guys never learned tautomerization when you learned about alcohols in 105. So we'll spend a little bit of time talking about that today. So ketones and enols are within equilibrium with each other all the time. And we're going to see that in the presence of catalytic acid or base, we can get the enol form to show up. Although generally speaking, it's not as common. We usually see about a 10 to the 4th to 1 ratio, thereabouts. So you don't really see the enol very much, but it may help certain things happen a little bit more easily. For example, if we take a look at a dione, the diones actually exist more as the enol form. We're going to see that, interestingly, if we just put the catalytic acid or base one of them forms the enol, and interestingly enough, this kind of forms a kind of six-membered ring, right? And six-membered rings are stable. It's not a full ring because that's a hydrogen bond. In blue there. And so we're going to see that this is a roughly like, I don't know, 3-to-1 ratio. So we do see that this one prefers the enol form because its enol is able to hydrogen bond with itself in a kind of six-membered ring, pseudo six-membered ring. And so, while it's not terribly important that we focus on this, the idea of tautomerization, the process of going between these two, is important. As we've seen it in previous reactions, right? It can help stabilize something. Particularly if you make an enol, it can rearrange itself to the ketone. It happens, in reverse that way. And we're going to see there are other reasons that we might prefer one form over the other. For example, here is an enol, and here is the corresponding ketone. Which one of these do you think would be the preferred form? Which do we think is more likely? The one with the double bond oxygen? Why? More stable, why? So you change your mind? Okay, so why is then the other one more stable? And why don't we touch the ring? Okay, well, these both have six-member rings, but what's special about the one on the left? Say the freaking magic word. Begins with A. Aromatic, yes. So we see that this one is a greater than 10 to the 5-to-1 ratio. Um, so because of the aromaticity. Yeah. So, Eric, you had the right idea. But the word aromatic is the one that you're looking for. So, yes, you want your alternating, your conjugation there. Remember that within the benzene specifically, the continuous pi system is especially stable, more so than just plain old conjugated things. So, yes, your aromatic one will be much more prevalent. So, and so this one probably you don't even need the acid or base to happen. Like it's pretty much gonna go like all the way. So, that's some stuff about that. This how this might happen if we want to take a look at a mechanism. Oh, that's ugly. The word tautomerization. That's a U there. Let's fix that. U. Ketone, enol, These are called tautomers of each other. And we'll look at the mechanism, and then we can see. So in acid or base, it's roughly the same idea. So in acidic conditions, where's Bailey? Oh, she's by the door. Okay. Acidic conditions, we have our ketone gets protonated. And then we have some resonance here. And then we have our good old-fashioned carbocation style elimination. And that leads to the product. These are equilibrium, of course. We see that these are tautomers of each other. So this is why it's catalytic, by the way. You have the acid form protonates your ketone, and then water comes in and deprotonates, releasing a new H3O plus molecule, right? So we're going to see that as a result, these things can go in between each other's forms. And we saw that for just plain old acetone, that's about a 10 to the 4 to 1 ratio, where we see this. But we see that these are called tautomers of each other. These are a special kind of constitutional isomer. These are tautomers. So if you remember various types of isomerism, you have stereoisomers, where we had enantiomers and diastereomers, and we had identical molecules, of course, rotamers, conformers. Now we're introducing a new one. This is a type of constitutional isomer. Constitutional isomers have the same atoms, but they're arranged differently. And so we, in fact, do have a different arrangement of the atoms, and so these are called tautomers. All right, so ketones and enols are tautomers, and the process by which they interchange themselves is tautomerization. And we're going to see that it can happen with base catalysis as well. This is the H plus version of the mechanism. The OH minus version we can do as well. There's not really a preference for one over the other. Base one's a little bit easier. Notice, again, it's catalytic, reversible, reversible. Just catalytic, so we use hydroxide to deprotonate, and then we take water and protonate. And so it's a still a catalytic process, so we use our hydroxide, then regenerate it, and so we end up with that. All right, in theory also, I mean, technically this resonates, but I had already done the resonance, but we'll be okay with that. So again, here we have tautomers. This is base catalyzed, the base catalysis mechanism for that. All right, so it can happen in either acidic or basic conditions. You really just need a small amount of base there. Cool. Any questions on tautomers before we actually start our first reaction for this? By the way, Bailey's finally like behaving. I'll take a picture so you can see her. Bailey, look up here so they can see you. Oh no, she's run off. Okay. She knew I was going to take a picture. All right, we good with tautomerization? It's the process by which they convert between each other. So for any ketone, you have a corresponding enol. There's going to be some ratio of which you have your ketone and your enol form. They will always both exist, right? And sometimes that ratio is gigantically skewed. For example, this one heavily favors the enol form. This one is a 1:3 ratio, so you have both at once in fairly large proportions. In the top one here, we have mostly ketone form. So it's just the point of this is to have you understand that both of these will always be present in whatever amounts they may be present in, but they're both going to be there. And how you get between the two is tautomerization. So it's just the process by which a ketone and enol are interconverted. Right, and so we're going to see that sometimes I'm going to just use one arrow and say tautomerization, and poof, now we have the either ketone or enol form of something. So, like if you remember way back when, I don't even remember when we were talking about it, but we did something that tautomerized to form maybe an aromatic species way back when. But that's the idea. So it's if you understand the process, then that lets me just say, I can just say tautomerization, poof, now I have the other form of whatever I want to talk about. Interchange, I think, would be a better word. Yeah. All right. Let's talk about them. So, let's do it. Let's talk about reactions at the alpha position. And the first one will be halogenation. We're going to see that if we take, I'm going to take a symmetric one to start. If we use acid and a halogen, we're going to end up producing the halogenated form at the alpha position. This one is going to be kind of the less useful way of making or of brominating. We're going to have better reagents for this as well. This will also work with chlorine or iodine. And we can take a look at the mechanism to see what's happening here. So this is an acid-catalyzed process. So just like before, we're going to make sure our mechanism is consistent with an acid-catalyzed process. So let's take our, let's say we're going to have our acid here. First step in an acid-catalyzed process is protonation, as always. As always, so we're going to lose our water here. Just like with the tautomerization, we're going to do some resonance just so we can have the elimination happen. This is just resonance. We have our carbocation. And now we will have our water come in. Deprotonate that. So because we are making the enol here, I can save all this space by just saying, this is the purpose of understanding that word, is I can just go, tautomerization. And poof, I have saved myself 3 steps of mechanisms writing. So that's the purpose of learning the word tautomerization, is because just like with a proton shift, like a proton shift, yes, I can say 3 steps, deprotonate, protonate something else, right? I can do the same thing with tautomerization. So it's a way of making it so that we understand exactly what's happening in a very quick manner. So that's the first 3 steps of this. 1, 2, 3. Yeah, 3 steps is tautomerization. That's all that's happening here. And now once we have the enol form, now we can actually react with it. Because we're going to see that this thing is going to be nucleophilic. We'll have our halogen of interest. Close this down. That causes our double bond, the ene part, to go ahead and attack the bromine and kick out the other one. Oops, this should be the double bond. That's the ugliest H I've ever seen. Alright, so we will now have a bromine on this thing. We lost a Br minus. And then we will have the last step in our acid catalyzed mechanism will be the regeneration of our acid by deprotonation. So the last step, deprotonate. I will I'll put this up as well so we can see. So we will have ended up with our product. So I can simplify the mechanism by just saying tautomerization. That's the idea here. So anyways, once we are at the enol form, we're going to see, generally speaking, we're going to use the enol form as our reactive species. And then we're going to go ahead and have it attack. It's a nucleophile, so it's going to go ahead and attack the bromine, which is going to then produce our brominated species, which then will be deprotonated, regenerating our acid that we used in the very first step. And remember, you can use chlorine or iodine with this as well. They will both work. And so you'll end up with whatever halogen. You can't use fluorine, of course. As always, fluorine is just too reactive. The reaction is just not observed with fluorine there. And we're going to see that this process, the acid-catalyzed halogenation of the alpha position of a carbonyl compound, will have some regiochemistry associated with it as well. We're going to see, if we take the same molecule, put a methyl group on there, we're going to have two potential products, right? We have two sets of alpha protons. We're going to see that the major one will be the more substituted one. Because our enol, the enol form, we have two potential enols. Excuse me. That's enol 1. Is it okay if I go horizontal for this part? Are we okay with the mechanism for the first half there? All right, well, yeah, we're good. Okay. Okay, so we've looked at the two enols that form. These are the two potential enols that we can get from tautomerization of this ketone. And we can see here that this one is more substituted, which means more stable, meaning that we're more likely to get the product that arises from that enol. If we use the other enol, we get the minor product because the double bond there is going to attack the bromine and it'll be on the left side of the molecule, right? So we're going to see that the major product for acid catalyzed halogenation, you'll end up with your major product arising from your more substituted enol, which will be the more substituted side of your ketone. And of course, if we were so inclined, we could deprotonate this and eliminate, but blah, we don't need to. Let's look at a better mechanism for doing this, especially if we have carboxylic acids involved. No, we don't have time. So we'll start next time, I guess. So that's the idea here. So you can put a halogen on an alpha carbon using acid as your catalyst here. And we're going to end up getting this to happen. We're going to see it can happen in basic conditions as well, although we have to be careful sometimes. So we'll see that next time. The base catalyzed halogenation. And then we'll look at the HVZ halogenation of carboxylic acids. That's what we'll look at next time. We'll start there and then we'll keep on going. Maybe we'll get to the aldol reaction. That'll be fun. So we'll go from there. So any questions on the halogenation idea? These would be the intermediates for the mechanisms going to these products. Yeah. So, because remember that, like, if we were to look at the mechanism, we got a second, let's do it. Look what I can do, aha! So I can cheat on my mechanism. Now, if I've got this one, I can have it attack the bromine, and now we have our product. Oops, I forgot the important part here. So we'll end up getting our brominated product, right? I'll leave it protonated for now. Who cares about the deprotonation? Remember that this also tautomerizes into the other species, which then can attack a bromine. and get the minor product. Go ahead. Both. Well, it's not a chiral center on the bottom molecule, but this one would be plus minus here. Because an alkene, remember, is sp2. It can attack the bromine from the top or the bottom. So there's no, in this case, there's no, you'd get a racemic mixture. And yes, if the bottom molecule, if this were a chiral molecule, yes, you would have a racemic mixture there. And so again, this is the major one down here. This is the minor one up here. These are the tautomers. There are two different tautomers of this molecule, and they can both react, but the one that's more stable will lead to the major product, which is putting the bromine on the more substituted alpha carbon. All right. Cool. Alrighty, well then we will continue with this next time, and we'll go from there. So enjoy your day. Maybe I'll see you at office hours. Is anyone planning to come, by the way? I have to decide if I'm going to do 12:30 instead of 12:15. I assume, Eric, you're probably going to be there, right? So 12:30, yeah, let's do that. So I'll do my office hours at 12:30 instead. So I'll see you guys then if you want. Okay, cool. We'll continue on Wednesday.